AAPG Unicamp Student Chapter is a group of undergraduate and graduate students in geology, geoscience, and petroleum engineering, hosted in the Institute of Geoscience from the University of Campinas, Unicamp, in São Paulo, Brazil. Our main aim is to provide academic and professional capacitation to our members, to the university community, and to the people out of the university, contributing to a better society. We focus on academic and non-academic activities, approaching petroleum geology and other related geoscience subjects. We are also engaged in social activities, promoting social campaigns and spreading geoscience to the society through the Earth Science Week activity. We are very proud to have reached about 240 people during the Earth Science Week 2019. We enjoy working together and give our best.
Hello everyone, I believe you can all hear me and see me. My name is David Murray and I'm a member of the AAPG Unicamp Student Chapter. I'll be your anchor for today, moderating this section on enhanced oil recovery. So you're welcome to this section, which will be centered on enhanced oil recovery, alternatives for the particular reservoir challenges of Colombian oil fields. So this presentation today is going to be in two sectors. We're going to have the actual presentation by Dr. Ugo, which would last for about 40 minutes. And then after we would have a question and answer section, which would last for about 10 minutes. So we'd encourage you to kindly drop your comments and your questions on the comment section just below the screen. So today we have Dr. Ugo with us. Dr. Ugo will be taking us on the topic enhanced oil recovery alternatives for the particular reservoir challenges of Colombian oil fields. Dr. Ugo is a petroleum engineer with the Industrial University of Santander. He holds a master's degree in chemical and petroleum engineering with specialization in reservoir engineering from the University of Calgary. He's currently a PhD candidate at the University of Calgary, and he possesses extensive experience in the upstream and midstream operation, from research to wireline operations, improved recovery methods, oil transport treatment. He currently serves as the head of department at the Ecopetrol's Colombian Petroleum Institute Innovation and Technology Center. He has extensive teaching and research experience in recovery methods with numerous intellectual products. Without wasting so much of our time, I would like to give the platform over to Dr. Ugo, who will be taking us on this insightful presentation. Thank you so much, Dr. Ugo, for having us.
Thank you, David. Thank you, everyone, for the invitation. I'm gonna share my screen and let's the fun start. Okay, let me know if you can see my presentation, my screen. Can you see my screen right now?
Yes, we can see your screen.
Okay, so as David pointed, I'm going to talk about EOR alternatives for the particular reservoir challenges of the Colombian fields. Basically, some insights that I have collected through my experience in EOR in Colombia. So I'm going to start giving you guys a little bit of an idea on what the Colombian oil profile is, what kind of oil we deal with in Colombia. Generally, I'm going to talk about how to increase the recovery factor. We're going to do a little bit of a comparison between IOR and EOR. Then we're going to go deep on why EOR, some concepts and alternatives to pass to EOR technologies incorporation process, which is important to understand how we proceed with analyzing every alternative we have to increment the recovery factor. Then I'm going to talk about the EOR in Colombia today, what we have implemented, where we are heading to, what are the biggest challenges in Colombia in terms of EOR. So with those challenges, what are our research proposal for these EOR challenges? At the end, I'm going to close with some final conclusions and remarks. So let's see what we're dealing with in Colombia in terms of oil. So we currently have around 55.3 billions of barrels as oil in place, which we still have underground 38.2 billions of barrels underground. We have fields in mainly 4 or 5 basins throughout the country. Our recovery factor is around 19%. We have 2,000 million of barrels of proved reserves. Our current production is around 886,000 barrels of oil per day, and our internal consumption is the 40% of that production. In the regional area, we are just one more players behind Venezuela, Brazil, and Ecuador. We are right in the same level of production as Argentina itself. I'm going to have to apologize because I didn't have the time to translate from Spanish, but here we have our basins. We have Llanos Orientales, which is the biggest basin we have in Colombia, with 68.9% of the production coming from that basin. We have the Magdalena River, the superior, inferior, and middle valley, with a big portion of the production as well. We have the Putumayo and we have Catatumbo, which are the other two biggest basins in the country. But what is important here, guys, is that this is our map. This is Colombia. And the departments in black are the departments where the average oil production comes from heavy oil. And this graph here at the bottom shows how big is the percentage of our production represented by heavy oil, heavy and extra heavy oil. So that's an important point. We're dealing with lots of heavy oil. And the other important point is that 70% of that heavy oil comes from depths bigger than 6,000 feet, which makes difficult to implement technologies like steam injection, for example. So we need to find alternatives. We also have lots of intermediate or light oils in some of the other basins that needs to be taken care of as well. So let's see what we propose. Our target in Colombia is try to reach the 36% average world recovery factor from the 19% we are right now. And we're targeting basically the 38.2 billions of barrels that we still have underground. How to increase the recovery factor? So let's see and remember what recovery factor is, which is the ratio between the cumulative production and the total oil found in the reservoir, known as oil in place. We can refer it as actual recovery factor when we are calculating it as today. We can refer it as ultimate recovery factor. We are calculated by the end of the life of the field when the production reach the 0 barrels per day. We can talk about the economic recovery factor when we calculate the recovery factor when we reach the economic limit, which is going to vary depending on the economic environment. And the one that we use the most in EOR is the incremental recovery factor, because that's the one that's going to pay it off economically what we invest, right, in research and in implementation in technology for this incremental recovery factor. How can we increase that recovery factor? We can do a lot of things. We can do things near the wellbore area. We can do fracking. We can do stimulations. We can do horizontal wells. We can strategically locate the wells, or we can do infill drilling as well to increment the production. But we can also intervene at a reservoir level with this type of methodologies, the EOR, the enhanced oil recovery, that can be chemical, thermal, or miscible. And the main difference between these two, intervening the near wellbore area or versus going for the full reservoir, is the impact it has in the reserves, basically. Because when we have this baseline here and we go for these near wellbore stimulations, we're going to increase production eventually. We're going to accelerate production, but we're not going to get at the end more than we were getting with the baseline. When we intervene at a reservoir level, we not only get a bigger production rate, but we also get more oil out of the ground, more cumulative production, making a bigger impact in the recovery factor itself. So basically, we're talking about IEOR and EOR. IEOR is improved oil recovery. EOR is enhanced oil recovery. And IEOR is basically virtually all but the primary processes, including infill drilling. It's everything we do to increase production. EOR is part of the IOR, basically because we not only increase production, but we also impact reserves. And that's basically because we intervene deep into the formation. That's basically the main difference. So what's EOR? What's enhanced oil recovery? And we go to the basic definition that we can find in Wikipedia, which is the implementation of various techniques for increasing the amount of crude oil that can be extracted from an oil field. So everything we implemented to increase the recovery factor, basically. And why it's important to deal with EOR? First, worldwide consumption is increasing around 2% per year, and we're gonna see some facts about this energetic transition we're talking about lately in the world. Reserves are generally not replaced. If we want to replace the reserves we are consuming, we need more giant discoveries. More wells doesn't mean more oil, and we saw it before, right? When we increase the number of wells, we are accelerating production, but we're not getting more oil out of the ground. EOR applies to already discovered reservoirs. We don't need to make an extra effort finding more resources. They are already underground, and we just try to get them out of the underground. Not effort required for searching more, not exploration. Infrastructure is generally in place because when we go to EOR, we are already dealing with fluids in the surface. The trade markets are already established. We are selling currently oil, and we're just gonna sell more of this oil. Cost-efficient technology is already developed and available. It's just a matter of customizing. And that's what I'm trying to present here, is how to customize what is already in the market, what is already in the science, particularly for what we have, the challenge we're facing. 60% or generally more of the oil remains in the reservoir after secondary recovery. So that's important. So nowadays we're hearing a lot of energy transition. We're saying, okay, we're trying to find energy sources more environmentally friendly, right? So again, my apologies, I didn't find this picture in English, but this is the percentage of the source, the energy source in 2019, where 31.5% of that resource, it's the oil, right? And this is the projection for 2045. We're talking around 20 years in advance. And it's going to change. It's going to be reduced, but only by some points to 27.5. And which is what is making it going lower? It's basically because the developed countries are decreasing the oil consumption, and developed countries are the less population in the world. Non-OCDE countries like South American countries, almost all of the South American countries, are actually gonna increase that percentage of oil usage. So here the message is not that we don't research on finding more environmentally friendly energy sources, but we have to deal with the reality that we are still consuming a lot of oil, and that transition is not going to take a couple of decades. It's going to take a little bit longer, and in the meanwhile we need to keep the economy going, and we're going to need oil, and then we need to still find ways to get that oil from the underground. And that's the news I wanted to share with you. So what are those conventional EOR methods? We had chemical, thermal, miscible, and in the chemical and the thermal, we can have nowadays nanotechnology trying to improve the impact of all these chemical and physical processes going on with the injection on some fluids into the ground. We can inject surfactant polymer or alkaline or what we know what ASP. We can do in the thermal, we can do steam, we can do air injection or in situ combustion. In the miscible, we can inject CO2 solvents. We can do a lot of things, inject a lot of things to increase the recovery factor. How do we implement this EOR? So basically we have this, what we call the technology incorporation process. What we try to do is with this process is to reduce the risk while we improve the recovery. And that we achieve it by going step by step. First, implementing a pilot. And then when we have that pilot and when we try it in the field with operational parameters from the reality, we can go and try to expand that technology to a commercial level, to a full field level. And what are those step by step? So first we gotta go and try to do a screening process, see what kind of technology applies for our particular case. In our case in Colombia, in Ecopetrol, we have Eco EOR, which is a tool that we use to do that screening by two means. One is the screening itself, when we get the basic properties of the reservoir in a study, and then we compare it with all the different technologies developed. We have a database with thousands of fields going through EOR, and we choose, here you can see in green, the technology that applies to those basic properties of that field in a study. And it's going to give us which is the biggest one, the more important one, the principal one, and what are not that good for that case. The other way we can do it is with analogies. With the same basic properties, the system, the database, is going to give us the list of fields with these similar basic properties that went through EOR and which of these EOR processes were successful. So it's going to give us, we can either go and find the technology that applies to that basic properties, or we can go and find a field where a technology was already applied and it was successful that has the same basic properties as our case. Having that screening, we go to the next step, which is the experimental analysis. And what we look for that is that we do fluid, rock fluid, and some other experimental analysis that is going to give us compatibilities. If we inject something in the reservoir, are we going to avoid precipitation? Are we going to have emulsions? How the thermodynamics work, the mixtures and phases properties. In the rock fluid, we see displacement efficiency. How good is my displacement process within the rock? It's in a core level, right? But it's going to give us some ideas. And some other interactions that as absorption compatibilities that are very important, especially in chemical process. and some other like geomechanics, material integrity, because remember that it's important to get the oil from the underground, but it's important to know what we're gonna do in the surface with that fluids. How are we gonna handle it? What kind of fluids are gonna have in the surface that we're gonna have to deal with? So that's important in the experimental analysis as well. Then we go to the forecast simulation, and that's basically when we get all that we have from the geology, right? With the static model, we get all this information from our experimental phase, and we have this kinetic model in some cases where the process is chemically heavy, chemically complex. We're gonna need that kinetic model because we need to do all the stoichiometric required to see what we're gonna have at the end. All that is combined into a simulation model that is gonna let us to have our injection profile, our production profiles, but also, and more importantly, what kind of fluids are gonna have in the surface that we're gonna have to deal with. That is gonna allow us to forecast in terms of amount of fluids, but also it's gonna help us to design the pilot itself. And how we design that pilot? We're gonna have to go through step by step. First, we're gonna have a conceptual engineering, then we go to the basic engineering, and then we go to the detail engineering. In the conceptual engineering, we just get the components of the surface and the well facilities. And the basic engineering, not only the components, but also the location of those components within the surface facilities. And the detail engineering is gonna give us measurements, distances, material types, etc., for us to have the pilot ready for the fluids we're gonna produce. The pilot test main objective is to obtain as much information as possible to characterize the EOR process and evaluate reservoir response to it. Once we have the pilot in place, this is the most important part, the monitoring of the pilot. Why is it important? Because through monitoring, I'm gonna not only test if the technology was successful or not, but also it's gonna let me to optimize. Because one thing is when we see in the experimental, in the lab, right? When we're dealing with portions of the reservoir, with portions of the fluids. Now we're talking about a field. We're talking about real operational parameters. So that's very important to understand. The pilot itself it's a small lab, right? And it's the only way to get real response from what we're gonna face full field. So what we do in the monitoring section, we do we measure flow, we measure pressure, temperature. We decide if we're gonna have observation wells. We use tools like well logging. We do production tests. We can go seismic, microseismic. We can use tracers, and obviously we have to analyze doing quality control of the fluids produced. So understanding how we test these technologies to see if they apply to our reservoirs, let's see where is Colombia right now in terms of EOR. So the first step is obviously the water fluiding, because we know that water is the fluid that is more available in the world. So that's the first thing we're going to use, is the more compatible fluid that we can introduce to the reservoir. So Colombia has gone through water fluiding a lot in all the basins. Basically, we're talking about light oils, we're talking about intermediate and heavy oils in all of our basins. So we are doing water fluiding since 1957. And we're currently going through water injection even in the heavy oil fields. Why water fluiding? As I say, it's the simplest way. What we're doing water fluiding is we're looking for improving mobility ratio. We're trying to get the oil pushed with water, right? But in that process, we have a lot of issues with that displacement, right? We have the breakthrough of the water sometimes very early, as we see in this picture here. We have fingering, viscous fingering, when we have the water going into the oil phase and getting ahead of it and having water in the production wells earlier in the year. So Colombia, as I say, has gone through the water flood a lot. We are in a mature stage of the water flooding in our country, but we need to understand we still have room for opportunity in water flooding, and that's why it's the first thing that I'm going to let you guys in your mind is that we still need to improve the water flood. Some other things we're doing in Colombia, we have steam injection in Teca-Cocorná. It's in the Magdalena Basin, inferior Magdalena Basin, sorry. We have tried gas injection. We have tried a lot of chemical EOR. We have tried not only polymer flood, but we have also tried conformance, which is a way to correct the mobility in water flood and in polymer flood. We have tried in situ combustion in 2 fields. And we have tried, as I say, gas injection also in Rio Ceibas in the superior basins. This is the status we have in Colombia right now. So we have steam floods pilots, 2 steam flood pilots in the Magdalena basins, in inferior Magdalena basin. We had cyclic steam stimulation since 1975, I think. We're doing cyclic steam stimulation in heavy oils. Here, we have polymer flooding in the Magdalena basins as well. We're trying pilot-wise HPAM, which is the more common polymer flooding. We have tried conformance. We do CDG pilot and field at a field level in DINA. We have tried Marcid gels, and we have tried bright water as well. In CO2 injection, we have tried WAC, and we have tried CO2 by itself. I'm going to talk a little bit about each one of the challenges in each one of these technologies. And we have tried in situ combustion in 2 pilots. One is the STARS technology, developed by an international operator. And we are currently closing the dry air injection pilot in Chichimene field. So what are the challenges in each one of these technologies? For steam flood, basically, as I said before, we have tried the cyclic steam stimulation for a while. Now we are in the latest cycles. Some wells have gone through almost 14 cycles where we basically are producing a lot of water and a little bit of oil. So we need to optimize that. We are looking for alternatives to optimize that cyclic steam stimulation. We have 2 steam flood pilots in Colombia, very successful, but the problem is that to go full field, we're going to need more gas, and we don't have that gas in Colombia right now. So we need to find ways to get that gas or to reduce the gas requirements to be able to proceed with the steam floods. But we also have another part, and it's important. Colombia signed the Paris Agreement, and we need to reduce emissions as well. So that's a hint on where we can get the gas that we need to go steam flood, and I'll talk about that a little bit later. For polymer flooding challenges, as I said before, we have tried pilots in heavy and intermediate oils. When we're going to polymer flooding, what we're trying to do is to improve mobility, but improving the water viscosity, adding polymer to the water. In those pilots, we have gone, we're doing very good in those pilots, but we have 2 main concerns. One is mechanical degradation, and that's basically when the polymer goes through the valves to be injected within the well, within the reservoir. The pressure, differential pressure in that valve degrades the polymer, decrease the viscosity, and sometimes very aggressively. And for the fields where reservoirs with high temperature, we are experiencing biological degradation. And that's basically because the bacteria likes a lot the polymer. They feed from polymer, and that's our biggest problem. So we're facing those challenges with polymer fluid. With in situ combustion itself, basically, we're preparing ourselves for all the possible problems, operational problems mainly that we may face. Problems like incrustation, asphalting production, emulsions, low injectivity, sand production, and corrosion. And we haven't faced it yet in our pilot, but we know that's going to happen sooner than later. And we are preparing for that. That's the challenge we're facing with in situ combustion. With gas fluiding challenges, basically gas is one of the most effective EOR processes. Miscible or immiscible both work very good in intermediate oils. But the problem that we have in Colombia is that we don't have CO2. We don't have natural sources of CO2. So in order for us to inject CO2, we need to produce it, right? And that's very expensive right now in Colombia. And that's how we're heading to trying to get these CO2 sources more cost efficiently. So having those challenges, let's see how we are working from the research to deal and try to resolve those challenges. So let's start with the water fluiding. For the water fluiding, we have the mobility control, and for that we have deep conformance. We're researching in deep conformance, and we're researching in tracers. Those two work together, and I'll explain later why. And then we want to optimize water fluiding by modifying wettability, and that's by the use of smart water. So let's see first all the proposals for water fluiding. So tracers, we can do single well tracers, we can do interwell tracers. Basically what we do is we put some chemicals in the well, we inject it into the reservoir, and we see the response. In the single well, we try to see the response in the same well as we injected. And basically the main purpose of the single well tracer is to get the oil saturation near the wellbore and see what's the impact of whatever we want to do in the well in terms of reducing the SOR. And in terms of the interwell tracers, basically we want to verify connectivity and flow preferences within the reservoir. We calculate the arrival time in the production wells, and we use different kind of tracers. We use fluorobenzoic acid, we have quantum dots, and basically this helps to significantly characterize the reservoir and the flow preferences within the reservoir. Once we characterize the flow preferences, we can see where we have to put to block those preferences in order to have a more homogeneous process, whatever we're injecting, water or polymer, right? And that's when we use the conformance alternatives that we have. The conformance alternatives is basically gels and some other chemicals that we inject. We put it in the reservoir, and they have an activation time when they basically expand, blocking these high permeability channels, making the water or the polymer that we inject to travel more homogeneous within the reservoir. Typical gels contain around 0.5% of polymer, 0.01 cross-linker, which is the one that makes it thicker, and 99.49% of water. And we have tried in Colombia CDG, Marcy gels, bright water, and we are just about to start the first pilot on small microgels. Smart water is a little bit more complex. We also call it low salinity water, and that basically what look for is a synchronization through salt content on the ionic charge, and that ionic charge is gonna make change the wettability and make it easier for us to have water flowing within the reservoir. We're just in the experimental phase of this. We're doing our fluid and our fluid rock. We measure capillary pressure, we measure contact angle, displacement efficiency. And with that, the thing with the smart water is that it's very customized. It's not that you find a formula and then you apply it to all the reservoirs. It's custom made for every reservoir. So it has a lot of experimental work before to go to the field and try it in a pilot itself. In terms of polymer fluid, besides all the mobility control and wearability modifications, as I said before, our biggest challenges are the degradation, the mechanical and the biological, and we're also looking for some alternatives. So let's talk about that. As I say, the mechanical degradation happens basically in the valve where we inject the polymer within the reservoir because of the differential pressure here. That basically breaks the chain, making it less viscous. So what we did in the surface, putting polymer, trying to viscosify the water, it just gets ruined in that valve. So we are working with the manufacturers of those valves, trying to get a design that allows us to keep as much as we can the viscosity that we put to the water with the polymer. We're very successful what we have tried, and it's again custom made. It's again for each case you have to try it and look for the valve that is going to work for that specific shear rate. We're working on additional prototypes. We're test design and execution in 2 fields. We are evaluating the massification, and we're just about to move to another field. For the biological degradation, we are working with biopolymers, and that's our polymers naturally based. Goma, Santac, scleroglucan, those are the ones of biopolymer that we are using. They are more than physical and chemically more stable than the HPAM. And those type of biopolymer, we need less product to viscosify the water. It's a little bit more expensive, but you need less. So at the end, it gets in equilibrium with the synthetic type of polymers. We're also trying polymeric surfactants as an alternative for polymer itself. With polymeric surfactants, we're not only improving the water viscosity, we're also reducing the interfacial tension, making the oil saturation going lower in the reservoir. So it's very important to know that we're trying to get these ones and tested experimentally for the same fields that we are testing polymer fluid. We're also working with nanohybrids, and that's we structurally modify polymer and make one structure, and that has the properties of the nanomaterials and the properties of the polymer. Right now, it's very challenging because of the cost and because of the synthesis routes that we have to use, a little bit complex. But we're on the way to have an in-house product that we're gonna try later this year or next year. Let's see from the steam processes, what are our proposals? For steam, as I say, cyclic steam stimulation is very inefficient right now, inefficient right now. So we propose the preformed foams. We are basically surfactant plus water plus nitrogen to form that foam in the surface, and then we inject it through the surface, from the surface through the well. And what it does, it goes to the space in the reservoir where the steam was going through all those cycles. It blocks that, and then when we go back with the steam is going to look for parts of the reservoir that hasn't been swept already, and it's very successful. We have a pilot test in Teca field with more than 25,000 barrels just for wells. Technical and operational capabilities, to proceed with full field implementation. We have a better energetic efficiency and revitalization of mature fields. We have the intellectual property of the foam generation system and the methodology, just because this device here that we put in the wellhead, it has the specific design that makes it the foam more, how to say that, stronger, is a stronger foam. We're also trying steam-based hybrid methods, and that's basically, remember I told you we don't have enough gas, and we need to look for a reduction of the gas requirement. So what we're looking is, we're looking after using the gas that we produce, the CO2 or the combustion gas that we produce from the steam generators, and re-inject it with the steam. So by doing that, we're reducing the amount of gas that we require, and that's basically what we're trying to do. We're trying to get the gas within the reservoir with the steam, and having the gas requirement reduced, so we can proceed with the steam flood easily. For the CO2 and flue gas, so remember that here the problem was that we didn't have enough gas, the CO2. So we have a lot of emissions. We have two main refineries in Colombia. We're looking for the different process that available in the market for extracting the CO2 for the flue gas, in order to have processes of EOR. This analysis is the one that we're going through right now, and basically we're trying to calculate if the new emissions after that process are bigger, smaller, or the same as the ones that we were having before. That's our main purpose right now, is to have an efficient, not only using the emissions from the refinery, but doing closed cycles of those CO2 and flue gas injection, so we don't have to replace the gas that we are injecting as much as if we were just floating within the reservoir. Finally, we have in situ combustion, and what we did, because we didn't have the experience already, we developed methodologies to create those problems synthetically within the lab. So we tried different ways to correct those problems, to mitigate those problems, and we have methodologies in place for that in case we face it. But right now, as I say, we haven't faced this type of problems in the pilot. We have been producing almost 2 years from that pilot, and we haven't faced any problems with emulsions, asphaltenes, or incrustations. As a conclusions and final remarks, I want to tell you that Colombia still have a huge opportunity to increase its reserves and production with resources already discovered, because we have such a lower recovery factor. By using the complete cycle of technology incorporation process, it is possible to define a real commercial strategy for EOR implementation in Colombia. EOR technologies, even having been implemented at a full field level, still have room for improvement by adjusting the technologies to the particularities of each reservoir. It's almost custom made. New technologies for the increasing of recovery factor must achieve economically feasibility, including the carbon footprints reduction. That is important, guys. Nowadays, anything has to go through that analysis. We have to include in those analyses whatever is going to cost us to reduce the carbon footprint. And finally, energetic transition that includes greener energy sources will still take some decades. Meanwhile, it is necessary to secure all reserves and production, because we need to have the economy going on, especially in countries like Colombia, where we still have some road to go through before to get that to that point where we replace what the oil is doing right now for us. That's all I have to tell you guys about what we are doing research-wise in EOR in Colombia. If you have any questions, I'm more than welcome to answer.
Thank you so much, Dr. Ugo, for that very, very insightful and knowledgeable presentation. We've learned a lot from your wealth of experience, and we are so excited to be here today. Basically, you've gone through a lot of very technical stuff. some of which might be a little bit too advanced for most of our audience. I mean, because we have a mixed audience of the graduate, postgraduate students, and experienced students as well. And we have a couple of questions which we are going to dive into right away. I don't know if you want me to read out all the questions or do you want to take
Yeah,
them one by one?
just go ahead and read it.
Okay, great. So we have a question here from Daniel. He said, "Thank you so much for your presentation. In your opinion, how complex can it be to expand from pilot projects to field level in Colombia? And what have been the challenges for their development?"
Thank you, Daniel, for the question. But basically, right now, the biggest problem has been the oil prices. Basically, definitely in a pilot level, we have been able to test and to optimize all the process we tried, and the economics are sometimes very difficult. Now, with the challenge of the energy transition that we're going through in Colombia, as I said before, that makes us even more challenging to make it economically, right? Technically, we can say we're ready to expand with in situ combustion, probably with polymer flood, with some of the conformance even. But our biggest challenge right now is all the economic process, financial process that we have to go through to include those parameters that we need to include now because of our compromises as a country with the Paris Agreement for that. But we are on the way, and we're proposing some research in terms of dealing with the flue gas from some of the processes, and dealing with the environmental impact that they may have. So technically, I say we're ready. We're trying to make it a good business for the country as well.
Thank you very much for doing justice to that question. And I wanted to add to that generally, yes, we're trying to reduce the carbon footprint of the industry. And I believe that you talked about injecting CO2. I mean, I think that that's going to be like the next phase for our industry, find a way to capture these emissions, carbon emissions, and try to inject them as secondary injection fluids, going forward. I don't know. So let's go to the next question. With the changes in the price of a barrel of oil in the world, how affected are these projects? Oh, you talked about the oil prices affecting.
Yeah.
Do you still want to say something about this?
With the prices we're dealing right now, what's the problem? The problem is that once the oil price go down, the first things that company wants to cut it's the expenses that they don't need, right? They want to produce, and they don't want to spend waste money or spend money on things they don't need. So research may stop when the oil prices go down. It's not what they should be doing, but it's what happens, right? Yeah. Once the oil price go up, we have to start again our research process, right? It's not that we're gonna start from the same point where we left. We're gonna have to redo some of the stuff. So even though our oil price right now is more attractive, right, and it may have an economically way to proceed with this, all these new factors for the environmental footprints, carbon footprints, and environmentally friendly technology that we are requesting, we need to reprocess all that financial parameters in order to make sure that it makes economic. It makes a good business for the country. Basically, we don't have. It also varies from technology, right? Because it's different the cost that you're going to invest in a process like in situ combustion compared to what you spend in a polymer flood, right? Just the surface facilities are hugely different. The reward it's only different. It's substantially bigger in thermal processes. But in terms of having an oil price is difficult. With the current oil prices, I think it's very feasible to go ahead with some of the projects, but we need to go through the analysis with all these new energetic transition things in the country.
Okay, thank you very much for doing justice to that. Another question: do you have? Oh, okay. If an EOR pilot is successful, could it be fully implemented in an analog field?
Um, it's a difficult question because it varies from field to field. It may not be it may not be even feasible to implement it in the same field, right? It all depends on the field conditions. Um, just from the pilot point of view, with the pilot you can go full field within the same reservoir, and may be or not be successful in the same reservoir. It all depends on the compartmentalization of the reservoir. It all depends on how much it varies the main parameters within the reservoir. And it's the same with the analog field. I will say, and on what we use in our screening tool, we use full field application to do the analog analysis. So I have to say it all depends. From the pilot results, I may go full field, and having a full field development of the technology, I may think it could work in an analog field. But pilot-wise, I'm not sure.
Okay. I hope Maria is satisfied with that. Okay, let's take the next question. This says, for the Brazilian offshore in the future, it will be necessary to apply EOR to increase the oil recovery factor since they are ultra water deep reservoirs. What recovery method could you suggest to be applied?
Okay, for that challenges are two main challenges, right? One is the surface, is the space available for surface facilities, right?
Yeah.
Complex processes may require a lot of surface facilities, right? But thinking that we have the area, we have the surface facilities, it all depends on the type of reservoir, right? If it's a heavy oil, if it's a light oil, if it's a heavy oil, we have to think on some thermal methods, not necessarily injecting heat, but it could be in situ upgrading, for example. But it all depends on the type of reservoir. If it's deep, definitely steam is not an option. I will think about air injection if it's heavy oil. If it's light oil, we could think on polymer flood, smart water, maybe surfactants.
Okay, just to extend his question about the Brazilian pre-salt reservoirs. I mean, from what we currently know, we know that the Brazilian pre-salt reservoirs are majorly carbonates. They are carbonates, and they have very high heterogeneity. So, how does this complexity in terms of geology affect the type of recovery method that can be used in speeding up production?
Those are very challenging because of the connectivity, right? EOR processes are very successful when you can count on the connectivity throughout the reservoir, because you're invading the reservoir with some fluids and you're hoping to sweep the reservoir with that, right? When we're talking high heterogeneity, it's very difficult to have that. In some cases, they use fracking, right, to have a better communication within the reservoir, and I think that would be the best way to go before to go and implement something that you hope is gonna invade the whole reservoir.
Oh, great. So again, I have another question. So you talked about communication within the reservoir, and for carbonate reservoirs, you usually have like secondary porosity, like voids and casts. And how do you think that these structures can affect the entire recovery method?
definitely they have a big impact, as I said before, because you have a good porosity. What you don't have is communication, right, among those
Okay.
pores, right? So the first thing is try to have that communication, and to be honest, the only way I could think that you can get them communicate, it's through getting some channels through fracking or to some other kind of a stimulation that you may use to communicate those pores and have a connectivity within the reservoir, right? Because it's difficult if you have isolated parts, and in the main principle of the EOR processes is floating the reservoir and getting swept, getting the reservoir swept, right?
Okay. All right. So I guess we don't have any other questions in our comment section. So
Thank you very much for the invitation again.
you're welcome. Thank you so much, Professor Dr. Ugo, for your time, for the wonderful presentation. Really appreciate this. The video will be made available to anyone who is interested on our YouTube channel. So I guess with this said, we've come to the end of this technical presentation, and I hope that we have a lovely evening. Thank you so
Thank you to
much.
all of you. Thank you to all my students, and have a great week. Bye.
You too. Thank you. Bye.